Um, so where we left off at, right? We were going through the details about the IEEE, which of course when I say IEEE, let me be clear, the IEEE version of Spanning Tree, right, which is of course the older version of Spanning Tree, and we went through the Spanning Tree states. Okay, we covered that. We covered what listening and learning covers. So please, if you guys did, please cover that. We talked about the 50-second convergence delay, right? We spoke about that, right? And that's very important when once we walk into talking about rapid spanning tree protocol, so RSTP. Okay. And so we we've learned, right? And I think we've proven, right? Because of course the internet's been up so long, is that the original spanning tree worked amazingly, right? Um, but with anything, right? In hardware or software, computing in general, right? Um, Capabilities improve, right? And with those capabilities improving, right, the network has to improve as well, right? Um, so we're going to get those new protocols that emerge that take advantage of these new capabilities. The thing that came about from Spanning Tree with the advancement of technology, right, is the improvement of Spanning Tree, which which spawned the introduction of Rapid Spanning Tree Protocol. Okay, and just to be technical, right? Um, you can look that up, right? You can look up what Rapid Spanning Tree Protocol is, has its own protocol in a document by looking up on Google the IEEE 802.1W. Okay, so the thing is, right? Let's try to compare what's the difference between spanning tree and rapid spanning tree, and what's the similarities, right? So the thing with rapid spanning tree, right? We have rapid spanning tree and spanning tree, right? They both elect the root switch, right? And they use the same rules, right? And the tiebreakers that you guys learned about. Rapid spanning tree and spanning tree, right? Those switches still select their root ports with the same rules, right? Rapid spanning tree and spanning tree elect designated ports on each LAN segment, right? With the same rules and tiebreakers. Okay. Um, Last but not least, right? And this is where it's different is rapid spanning tree and spanning tree places each port in either forwarding or a blocking state, right? Now, in terms of you know syntax, right? And of course, words that are being used. Spanning tree calls it a blocking state, what have you. Rapid spanning tree, it calls the blocking state the discarding state. Okay. All right. So let's go ahead. One second. Let's go ahead and let me make sure I have everything I need. Okay, yes, I do. All right. Sorry guys, looking at the notes again. Um, so we talked about how you know, how rapid spanning tree works a lot like regular spanning tree, right? It has that one difference or what have you, right? So it has a lot of similarities, right? But the big reason, the overriding reason, right, of why rapid spanning tree was created was convergence, right? Spanning tree takes 50 seconds, right, with default settings to go ahead and converge, right? With rapid spanning tree, right? What convergence looks like within a spanning tree topology is 10 seconds. Okay. So, how was it able to do that? How was it able to just do that improvement of convergence being 50 seconds instead of 10 seconds? Right? Rapid spanning tree adds a mechanism by which the switch can replace its root port without any waiting to reach a forwarding state. Right? Also, rapid spanning tree adds a new mechanism to replace a designated port without any waiting to reach a forwarding state. Okay. And last but not least, rapid spanning tree lowers the waiting time for cases in which rapid spanning tree must wait for the timers that you guys learned about. And you guys remember the timers, the hello timer, the max age timer, and of course the forward delay. Okay. So let's put a scenario out there, right? So let's say you guys have the diagram, and we the diagram that I've shown you guys, right? That we've got from the book. And imagine we have a failure, right? A failure on which a link remains up, right? But for some reason, right, the non-root switch stops hearing hello BPDUs, right? That it's been, listening and hearing and what have you, right? Let's talk about spanning tree. With this being the case, spanning tree requires the switch to wait for the max age seconds, right? And what did we learn about max age? Max age is 10 times the hello timer, right? Hello timer is 2 seconds, right? And of course, the max age is 10 times that. So 2 times 10 is 20 seconds, right? And so by default, right? Rapid spanning tree, it shortens this timer, right? So instead of it being 10 times, right, in regular spanning tree, in rapid spanning tree, the max age timer is only 3 times has the hello timer, okay? And additionally, rapid spanning tree can send messages to the neighboring switch to inquire whether a problem has occurred versus waiting for the timers, right? So you want to think of rapid spanning tree as more so a proactive protocol, right? In terms of error correction and failure detection versus a reactive protocol in regards to regular spanning tree and waiting for the max age timer to be done and then to go through all the processes of converting different port states and roles. Okay. All right. So you guys talked about we talked about the different port roles and we talked about different port roles within spanning tree. Let me go over what the different port roles um, are within rapid spanning tree. Okay. Let me okay, and you guys just follow me for now. Um, so the different port roles is we have a root port, right? Non-root switches, best path to the root. You guys learned about that. We also have an alternate port, right? And that is the port that will be used to replace the root port when the root port fails. Okay. All right. Um, then we have the designated port, right? The switch port designated to forward onto a collision domain. Okay. Collision domain, you guys remember, it's just a link. Okay. Um, And we also have, of course, the backup port, right? And this is a port that will be used to replace a designated port when a designated port fails, right? So let's take a step back. So the root port, right, that we learned about in regular spanning tree, it has a backup. It can have a backup port, which of course is the alternate port. And the designated port can have a backup port, which is of course the backup port. Okay. Last but not least, we have the disabled port, port in a non-working interface state that is anything other than connected up. Okay. All right. I hope all of that made sense. Right. Um, I know I have this diagram. Um, I'd rather do this in a live lab. So let's not, I don't want to go through talking through talking through this. Okay. So we'll wait to actually see convergence live within a live lab. So we'll do that on Sunday. Okay. Let's go through both discussing a couple more things of rapid spanning tree states and a couple of the processes, right? To be complete, right? Note that both rapid spanning tree and spanning tree have port roles and states related to ports that are not currently working. Okay. Those rules are both spanning tree and rapid spanning tree define and use a disabled port role for any port in a non-working interface state, right? And what this means, right, is for instance, interfaces with no cable installed or interfaces configured with the shutdown command configured. Okay. That is what it is. That is what it means as far as to be in a disabled port state. Okay. Well, I'm sorry, to be in a disabled port role, right, for this non-working state. Okay. Spanning tree uses the disabled state for such ports. Rapid spanning tree does not have a separate disabled state, but instead uses the discarding state. Okay. All right. Um, of course, we have this table that discusses, of course, the differences, the different port states between spanning tree and rapid spanning tree. I'll let you guys go over that within your own time. Okay. Um, Now let's talk about this, right? Um, Rapid spanning tree, right? Of course, with it being an improvement on the IEEE standard for of just spanning tree in general, right? All the improvements were related to improve the speed of convergence, right? But let's talk about what is actually happening, right? As far as the difference, right? The switch changes, right? And let me get my pencil right here. Let me go ahead and pull it out. Pencil. There we go. All right. So number one, right? The switch changes the timer it uses to time out MAC address table entries to be equal to the STP forward delay timer, right? Which is default 15 seconds. The switch transitions the interface to the listening state. We're talking about regular spanning tree, right? Remaining there for the forward delay timer, another 15 seconds. After, now we're at 30 seconds, just follow. After the forward delay passes, right, two things happen. All MAC address table entries affected by this topology will be timed out, right, removing the possibility of loops, right? And then the switch can now transition, right, the port to a learning state, remaining there for the forward delay time. So that's another 15 seconds, okay? After spending the forward delay time in the learning state, the switch transitions the port to the forwarding state. That is a long time, guys. A very long time. Okay. So we got speed improvements, right? We got speed improvements in regards to convergence and rapid spanning tree. Okay. We're going to have this lab Sunday to discuss it, to talk about it. Please read um, please reread chapter 9 to its entirety, so you guys can follow, because I want to have a open discussion as far as the differences between regular spanning tree and rapid spanning tree, right? Because this will be on the exam, okay?
Alrighty, sounds good.
All
Thank
right,
you.
guys. No problem. You guys have a great
Sounds
night.
good. All right, thanks,
You
David.
too. Thanks.
Okay, bye,
Bye.
guys.